Welcome to this OST2 lecture about verifying a TPM 2.0 as genuine. This lecture is important as foundation for learning how to enroll remote systems using a TPM 2.0. Why do we trust a trusted platform module for the security and trustworthiness of our systems? Going beyond the trust that can exist between people and companies, there is a standardized process we can use to establish if the TPM device we're using or the virtual TPM that we're using in the cloud is part of a genuine vendor. In this lecture, we'll focus on discrete physical TPM, but the same process is valid for a virtual TPM in the cloud. TPMs come with a digital certificate that we call EK certificate, provided by the TPM manufacturer. This is usually stored inside the non-volatile memory of the TPM. Sometimes it happens that a certain model or a certain TPM variant does not have that certificate provided in its NVRAM, and that is okay. We can fetch this certificate from the web server of the TPM vendor. How this works? The EK certificate contains the public key part of the endorsement key, and just in the previous lectures, we learned about the special properties of the endorsement key and how its seed is randomly generated at manufacturing time and stays the same throughout the life cycle of the device. This is also why we'll use it to generate machine identity in these lectures. We can establish a TPM is genuine when we verify the certificate chain of trust. Usually we have at least one EK template for RSA and one EK template for ECC, as we learned in the last lecture. And each EK variant has its own EK certificate. These certificates can be verified using the intermediate certificate of the TPM vendor. And that TPM vendor certificate is then validated using a root CA or a well-established certificate authority. In this course, we will not go in details about X509 certificates. We'll just look at the practical side of how to achieve the verification of a TPM device as genuine by using certificates. Here is the typical flow of the practical part of verifying a TPM. First, we need to generate the endorsement key and obtain the EK public part. Then, we need to obtain the EK certificate, and we can do that either from the TPM's NVRAM or from the vendor website. We'll give specific examples to the most common TPM vendors. Now that we have these two artifacts, the first step is to make sure that the public part of our TPM's endorsement key matches the key in the certificate. Afterwards, we need to verify the EK certificate has a valid chain of trust, going through the intermediate certificate of the vendor and reaching to the root CA, resulting in the verification of the TPM as genuine, because we instructed our TPM to generate the EK. Then we instructed the TPM to provide us the public part of the EK, and we matched it to the certificate that turned out to be genuine and valid, walking through the certificate chain of trust. Now we'll look closer into more details how this works. To generate the EK, we can use the TPM2 create EK TPM2 tool. Why are we doing this with tools? Because the process usually happens at manufacturing time when you have your device set, or when you have your system onboarded in your data center, and so on and so on. So it is likely that you would like some kind of automation, and the TPM2 tools are great for doing automation. Of course, this is also possible if you just use the steps that we learned in the previous lecture to generate the EK using eSAPI. For the purposes of this lecture specifically, we'll use the TPM2 tools because we want to understand the process of verifying a TPM using the EK certificate. The steps here are familiar from TC 1101, but just in case, we'll walk through the most important arguments. First, we need to preserve the context of our EK creation. We can do this by either persisting the EK into one of the persistent key slots by just typing dash as the argument. And then the TPM2 tool will automatically try to find the first available persistent handle to use. If a file name is passed, the tool will store a context file, and we can later use this context file together with the public part to restore our EK in the TPM. save load context is how the TPM2 tools worked, and we talked about this in TC 1101. Because we're generating a primary key under the endorsement hierarchy, of course, we need to provide the authorization value for that hierarchy. And remember, the default authorizations are empty. If you have changed your hierarchy authorization, make sure you set the new one. Then we need to specify our key algorithm, and this is up to your preference or application requirements. We have two main good options, RSA and ACC, and because we're matching the TCG templates, this usually means RSA 20,048-bit key or ECC P256-bit key. And there is a third option, key hash. This is an HMAC key that we'll not cover in this lecture. In order to easily verify the EK public key with the one included in the EK certificate, we will need to have the EK public part in nice readable form. And usually this is the PEM format. Thanks to TPM2 tools, we can receive the public part of the EK in that PEM format. We generate the EK as usual using TPM2_create EK. Then by using the TPM2_read public tool, we extract the public part of the EK and we instruct the tool to convert to the PEM format using the -f argument. The -q you see in both commands is for the tools to not print messages in the terminal. Instead, we'll just receive the result, which is the EK PEM. And of course, do not forget to provide the authorization for your endorsement hierarchy. Here we have an example output, the first command generating the EK, then using the context from the first command and generating the PEM formatted EK public key as a file. And here is an example of such file. Because we are using a Docker lab environment and TPM simulator, you don't have to worry for exposing your EK public part, which can be used to identify your machine. And we talked about the privacy concerns with EKs in the previous lecture. Now that we have our EK public part in a readable form, we need to also acquire the EK certificate. And this is most easily done by using the TPM2_get EK certificate tool. The tool performs several things automatically. First, it tries to retrieve the EK certificate from the well-known TCG specified NVRAM locations. Here's an example how to do that for a RSA EK certificate. We just specify the output to the file where we want to store the certificate, and by default, the tool uses RSA, so there's no need to do anything more. When we need to extract also the ECC certificate, then we need to specify twice the -o argument for storing certificates to file. The first certificate that will be stored will be the RSA certificate, which in NVRAM space is stored ahead of the ECC certificate. And then we'll also receive the ECC certificate as a separate file. Because the EK certificates come in their format, we will convert them in a more usable, readable format for us. Here is an EK certificate after it was converted to a more readable form. Here we can see the signature of the certificate that we'll verify later by walking the certificate chain of trust. In case the EK certificate of your TPM is not available in its NVRAM, you can visit the websites of the TPM vendors. Here I've shown the links to the intermediate certificates of the most common TPMs. Each vendor has its own way of providing the intermediate certificates, and I've provided brief instructions about this. There are also EK certificate bundles, and these bundles represent the intermediate certificates of all TPM vendors and TPM models out there. While providing some form of ease, these bundles might be difficult to verify as genuine, so they can pose a security risk. This is why we recommend using the vendor websites if you need to acquire an EK certificate. For completeness, we have to mention that such certificates include, especially the ones by Microsoft and in the IBM's TPM software stack. When you make the choice of how to build your enrollment and provisioning system, make sure to take this into account, that there are advantages and at the same time there are risks associated with using a certificate bundle. What we did so far, we obtained the artifacts that we need in order to verify if our TPM is genuine. Now remains to perform the actual verification step and confirm that the EK public key matches the one in the certificate and that the certificate is genuine. Because the EK certificate comes in their format, we're converting it to a PEM format. And from the PEM format of the EK certificate, we're extracting just the public key that we're interested in. From there, we already took the EK public key from the TPM using the TPM2_read public tool. And now we can just compare the two public keys using diff or any other tool. This way, we establish a link that the EK certificate we have and the TPM EK that is currently present are linked. To make sure that we're using a genuine TPM, we need to walk the chain of trust of the certificate and verify it. There is not only one way how to do this. We will concatenate and combine the intermediate vendor certificate and the root certificate. Then we will verify the EK certificate using that combined certificate. Virtual TPMs have some vendor-specific way how to acquire these intermediate certificates and also which are the certificate authorities to use to verify. Of course, there is also information in the certificate itself pointing to that intermediate CA, but there are quite nice blogs and how-to documents to verify a virtual TPM. So I would really recommend reading the cloud provider documentation about this. We're focusing on a hardware TPM, and in our case, of course, for this course, our TPM simulator. The process is very, very similar and the fundamentals are the same. It is just note here that VTPMs may have some vendor specifics. Since we're using a TPM simulator, there is no TPM vendor in fact. So we have to generate our own EK certificate to be able to verify the chain of trust with the EK on our TPM simulator, and this is possible. Here I want to thank Ken Goldman for providing me the correct steps to achieve this. We have two options, of course. We can generate an RSA 2048-bit key or ECC P256. And depending on our needs, we have two variants of this command, which is called this TSS create EK cert. This command is part of the IBM TSS stack and it is preloaded on our Docker Lab environment. There is a password for the root CA that is 4 times lowercase r. Once we have the EK certificate stored in our TPM simulator, and we can just extract it using the TPM2_get EK certificate as usual, as if this really came from a TPM vendor, but it is just a TPM simulator. And then using OpenSSL verify, we can verify the certificate chain. Here is the complete workflow to verify your TPM simulator as genuine and having an EK certificate. First, we need to create an EK because we need the public key part of that EK. Then we need to extract that EK public part in a readable form or in a good form for comparison, which in this case is the PEM format. Then we create an EK certificate for our EK. And remember, if we generated an EK of RSA type, then we need to generate an EK cert for RSA. This is important. Once we have generated the EK certificate for our TPM simulator, we can extract it as usual using the TPM2 tools. Then we convert the certificate to PEM format as well. We extract the public key from the certificate and we compare the two public keys. If they match, then the last step is to actually verify the certificate as genuine. And if that's true, this means we have a genuine link between the creator of the simulator to our EK that is in the TPM. And in reality, this would be the TPM vendor which provided this certificate and not us generating it, proving that the EK pub we have is genuine and it was created during manufacturing time. Here is everything we learned in this lecture, and this is just an example output of how it looks when we use OpenSSL verify.